All right, we are back. We are back with Module 5. Module 5, we're going to discuss network components and architecture. Again, basic network components and basic architecture. And when I say architecture, it's basically we talk about the flow of how data flows through a network. When we think about some of the common network devices that we're using within this class, in this environment, really your in-home Wi-Fi routers, layer 2 switches, as well as layer 3 routers, and firewalls, firewall appliances. If you're familiar with Cisco, they call these ASA, Adaptive Security Appliances devices. We're just going to cover these briefly, okay? So when we think about an architecture, this is really kind of a layout of how information or data flows within your network. And if we start kind of at the bottom, okay? Think of these at the bottom as user devices. These are your different individuals in your organization that have a computer or a printer or whatever it may be. Okay, just call them user devices. And those user devices are typically connected to some type of layer 2 access switch. We call them access switches. So you may see these in rooms. Let's say if you're in a school building where you have a lot of rooms. Each of these rooms are an office environment. Each room may have its own access switch. So let's say if you have 25 or 30 students in a class, they all have a computer. Somewhere in there you'll probably see a switch like this mounted up on the wall or somewhere. Those are access switches. So if you think about all of these as individual classrooms, and these are the computers that students are using. So then we build from that up to what we call distribution or aggregation switches. Still a kind of a layer 2 device. But what it does, now as you see, now we aggregate from the switches that are in the classrooms up to a switch, and many times this is in a wiring closet somewhere, right? So this is what we've got here in that wiring closet environment. And now as you see, we can break this out into different LANs. This right here switch could cover local area network 1. This switch could cover local area network 2. And right now, these two local area networks, they can talk amongst themselves, but they really can't talk to each other because we're going to need another device that, just like going back to our postal example, I have two disparate local area networks, so I will need some type of routing or layer 3 device to be able to have these two local area networks talk to each other. So that's what a core switch or a router, some type of layer 3 device that's looking at packets, that's able to now do inter LAN routing. Okay, so basic architecture, right? Start at the bottom. Like I said, we got our user devices, we've got access switches, and then we've got aggregation or distribution switches, then some type of core device that's able to route. Now this is all well and good so far, right? So far pretty good. I can talk in my own building, but that's that's going to be short-lived, because at some point somebody's going to want to be able to get out to the internet and do other things, right? So we want to be able to protect that. That's where we would put some type of firewall appliance. And this could be a multi-layer appliance, meaning that it could operate at layer 2, layer 3, or at application layers up at the higher layers. And we're going to get into this a little bit deeper as we go along. So this will allow us now, we can connect from here to the internet, and we can have firewall rules in place that will allow who can get or what protocols or what machines or what devices can actually now get out to the internet. We can also use this device to do other things with our network. Let's say we may have another local area network out here, and I call it the DMZ, a demilitarized zone. We do this quite a bit in networking, where we have a set of devices, or many times servers, such as your proxy servers or web servers, that are sitting here that are protected by this firewall appliance, meaning that people from the internet may be able to get in and out of here, but not this direction. Or I can have someone here, these local area networks could come here and get to access this here, because I could have an internet proxy server or a web server that's sitting here that's protected. So that gives me some layer of security protection with a if you think about DMZ, a demilitarized zone, where we have that piece in the middle that's protected. So that's a basic network architecture. You see this quite often in buildings and designs, and they can, trust me, they get much more elaborate. But just to understand that when you think about a switched network or routed network, where these components will fit in that architecture. So now when we talk about switching and routing concepts, you know me, I always love teaching with analogies, right? really, here again, let's keep this simple. Let's keep it, there's nothing hard. All we're doing is transporting information, transporting data, no different than any other transportation system. So let's, I'm going to use a water example, water transportation system analogy. You go, what? Water? Yeah, because the concepts are the same. Okay, let's say we have a water system, right? I've got a source bucket. Bucket here, you got a whole bunch of water in it, and I want to move that water to a couple of destination buckets. So I've got a pipe that runs from my source bucket over through this piece right here I call a faucet. It's really kind of a switch that can control the amount of water that can go to each bucket as well as the destination. I may only want water to go from the source bucket to destination bucket 1. Or I may want water to go from source to destination bucket 2. That can all be controlled by this faucet. And this is a hand because this is a water system and it's a manual water system. You turn the faucet one way or another to control the flow. That is really what we're doing with switching and routing. We're controlling the flow of information, of data, ones and zeros, bits, packets, whatever you want to call them, from point A to point B to point C. Okay? So let's break these down into some logical components or planes. We're going to call these planes, all right? So we have a management plane. What is the management plane? That's the hand. That's the human decision to adjust water flow. Somebody has to come with this idea and say, well, you know what? I don't like the way the water's flowing. We need to change that. That's a management decision that says, okay, we've got to change the water flow. So that's our management plane. Now, this faucet, that is our control. What's going to call the control plane. Okay, and that's what actually controls the flow and the direction of water within the pipes. And the data plane, this is the actual water itself that's flowing. That's the data. That's the actual stuff that's moving through the pipes. Okay, so we have 3 planes. A management plane, that's the decision-making piece. Yep, somebody says we need to make a change. The control plane, that's where that decision is put into actuality. That's where we make the decision to turn the faucet. And the data plane is the actual water. Got it? 3 planes: management, control, data. Now, let's take this and let's overlay it with a network. Okay, so we're going to look at a basic router design. Remember those 3 planes. Very, very important. You're going to see that here multiple times. So within a router, let's say this is my network router. I have the same thing. I have this management plane. At the management plane, that's where the policies, that's where your configuration protocols, things like SSH or NetFlow or SNMP, your simple network management protocol. This is also if you have worked with a router or with things like Packet Tracer, that's where your command line interface and your graphical user interfaces, they all lie here in that management plane. That is analogous, to that hand. Now, also the next layer in a router, we have a control plane. We also have similar things in switches as well. So we have a control plane. Now, this is where your actual routing protocols live, like open shortest path first or EIGRP, all these different routing protocols. Or if you're going to do, these are dynamic routing protocols, by the way, but if you want to do static routes, that's all lives here in this plane. And really what's really important is our information base, our routing information base. That's the table. That's where our neighbor tables and all this stuff that makes these systems work. This is the faucet. This is really the faucet. This is where all that data lives. Your databases that collects the data for connectivity. All that lives in that control plane. Then we have, the data plane. This is actually where now you have the forwarding table that says this is how data is going to flow, just like the water in the pipe is going to flow. So the same thing, management, control, data. Now what happens north to south? Our management plane, it talks to the control plane once we establish what kind of policies we want, and it actually talks to that control plane and says, okay, we're going to use OSPF, or we're going to use EIGRP type of a protocol, or we're just going to do static routes. All of those decisions are made here in that management plane. This is also where we start building those routing tables. Okay, so now let's take and build out our network a little bit more. Okay, so this was my router. Now the thing with routers, they learn other routers or neighbors. So let's say if I had 2 neighbors, router 1 and neighbor router 2. Okay, 2 neighbor routers, and they have the exact same thing. You see, they have the same planes: management, control, data in both of those routers. So what happens now east to west. We talked about north to south. Now let's look at east to west. East to west, within that control plane, the control planes of all the routers are able to talk to each other. So that way, when I set up like a routing protocol, it knows to look for the same routing protocol in neighbor router 1, look for the same routing protocol in neighbor router 2. So when we set these up, they know to talk to each other. This will make probably a little more sense when we actually get into packet tracer a little bit later on in the course, and you'll see as we build out network and we start using EIGRP, which is the inter gateway routing protocol, that will now know all of its neighbors. It's out learning all of its neighbors. Every neighbor, how you doing? How you doing? Shaking hands, go, good to meet you, nice to meet you. And it puts all that information into a routing table. Think about this as a database. In this table, it says, I know I got neighbor router 2. I also know I got neighbor router 1. And then neighbor router 1 is doing the same thing in his table. Well, you know what? I know about his network router, and it also knows that there's a neighbor router 2. So you see, now all these control planes are talking to each other. Then once they do that, now it knows how to actually start sending ones and zeros at the data plane level. So now it can start making forwarding decisions that I need to forward data maybe this direction based on where it needs to go, or I may need to send it to a router, neighbor router 1. So you see the same process of moving data works. That's no different than moving water in pipes or moving oil in pipes or the U.S. mail system. There's those layers. They exist. Nothing different. We're just moving information from point A to point B to point C. So now let's give you a minute to marinate on that. You may have to rewind a couple times, relook at that, but that's just a basic router and switches design. So let's talk about a little more advanced topic here. I want to just kind of open this up. It's called SDN. You may have heard this, software defined networking. Okay, this is really where we're moving to, and well, we've been there for a while actually in industry for a smarter way to do routing. Now, if you looked at if you remember from our last slide right there, everything was very discrete. Each router had all of those things in it. Software defined networking is similar, not the same, similar to virtualization, where now we break those layers apart, right? It's so we almost like we're virtualizing the network architecture. So what we have in software defined networking, still very similar. We still can pull the thread across. So we have an application layer. At this application layer, that's where we have our applications like OpenFlow or some of the same protocols exist. Our application programming interfaces or APIs, and this is abstracted from the actual routers themselves. Okay, this application layer can live on a central computer or a central network, outside. Likewise, the control layer is abstracted. It is not a part of each individual router. It doesn't have to be. It can be abstracted. So now all the routing protocols, the IP routing tables or static routing, or basically like that faucet piece, it can be abstracted or virtualized. Now, the infrastructure layer is where our routing decisions are made. So we have in software-defined networking, we call them APIs. We have northbound APIs. This is where our application talks to the control layer. The northbound APIs, applications talking to the control layer. Then we have southbound APIs. This is where now the control layer talks to a multiple infrastructure layer devices. Meaning, so now I can have this abstracted control layer controlling multiple infrastructure layer devices. So when you have hardware, network hardware that is software-defined networking or SDN capable, basically what it does, now it is looking for a centralized control layer to make the decisions on how it's going to route. Now, you may say, well, what's the big deal? Well, here's the big deal. Now, at a central location, I can easily reconfigure my network in multiple ways. I can turn individuals off where they won't even see a part of the network. And this is all done through software, through an application that I can make all these changes almost instantaneously, and it's very agile. And from a security perspective, it is very agile. It brings a lot of security uh, things to the table when we think about capabilities to the table. Because now, let's say if I want to do network segmentation and I don't want an individual user to be able to get to part of my network, I can make those decisions now at the individual user level. We can connect this up and tie it into our Active Directory account management. So not only can I set up ACL rules, I can now completely demarcate a user, saying that, okay, a user now, you can get to this part of the network, but you'll never see this. So it brings a lot of agility when we talk about software-defined networking. Like I said, this is a little advanced topic, but I like to open this up now while I'm talking about those multiple layers, because that same concept, once you pull the thread, if you kind of understand virtualization, how we abstract the layers of a computer, your hardware layer from the operating system layer, from the application layer, and we can virtualize those. So in a sense, we're doing the same thing with software-defined networking. So now, actually, decisions can be made much more agile about how data will flow through your network, and reconfiguring your network can be done on the fly, where in a classic environment, many times to reconfigure, it can take a lot of work, a lot of reconfiguring. So software-defined networking, hopefully you have opportunities to see more of this as you go forward. Firewalls, like I said, one of the things I always like talking about is firewalls. How do we protect areas of our network? Whoa, lost my handy dandy clicker. That's never good. So when we think about firewalls, what does the firewall do? Firewall prevents undesirable traffic from entering prescribed areas within a network. Firewall is a system or a group of systems that enforce access policies between network devices. So it does. So, if you think of it, the term firewall comes from, like just in apartment buildings where you got a brick wall in between apartments, so that if there's a fire, it hopefully will separate that fire, where it won't move from one apartment to another, to another. Hence the term firewall. But yeah, through that firewall, you can set up rules, access rules to allow certain types of traffic. You can set up access rules to deny certain types of traffic. So that's the beauty of a firewall, that you can become very granular on how to do those type of things. Different types of firewalls. Like I say, we have packet filtering firewalls. What is a packet filtering firewall? Actually, it's a router with the capability to filter some package content. Typically, these work at layer 3, sometimes layer 4 layers, where we're looking at either IP addresses or some type of protocol or port, the destination or source ports, and it's able to make decisions based on layer 3 information. A stateful firewall, like I say, and what these are, they monitor the state of a connection. If a connection is up, if it's down, if there's a data transfer going, so it can move things based on the state of the firewall. We also have things to call DMZs. I think we talked DMZs a little bit earlier. Yeah, a demilitarized zone provides inside network protection, for certain things, like say web servers, proxy servers, and you can set up rules to limit access on who can get in to those areas. NAT firewalls, like I say, now network address translation, that's what keeps, IP addresses private, like Class C IP addresses private, or other IP addresses, so that people on the internet can't see your private IP addresses. And we can set up NAT or PAT firewalls to do that, network address translation or port address translation. As well as, like I say, we're seeing more of these now, application gateways or application firewalls, proxy firewalls. These actually, they actually can now operate at the higher levels, from layers of the OSI model, layer 3, layer 4, all the way up to layer 7, application layers. Like I say, these can do a lot of filtering based on a lot of different things. So when we think about firewalls, they work on something called an access control list, ACLs, access control list. That's really what helps mitigate network attacks and control network traffic. Two types of ACLs, two typical types, a standard and an extended. So when we think about a standard ACL, like I say, it's doing a pretty simple match. And really these work mostly with your packet at the packet level, at the layer 3, layer 4. They examine the source IP address and the header information. Extended firewall ACLs, like I say, they're able to do a lot more. Now they can start looking at your source IP address, your destination IP address, source ports, whether you're looking at TCP or UDP, and the protocol type or whatever that may be. Now, this is what a it's kind of the syntax of a firewall rule, ACL rule. I'm sorry, looks like. If you're going to have the router, you're going to be in the enable mode where you're going to configure at the router. You're going to tell it this is going to be an access list. The US select is going to be a standard or extended. You just have one another, and then you're going to give it a name. You're going to name your access list. Another line you want to put in here would be: do you want to deny or do you want to permit? You want to let something in or let it not go out? You're going to determine what type of what the protocol is. Is it TCP? Is it ICMP? Whatever it may be, and then the address, your source address, and the subnet mask that you're going to use for that. ACLs. Now, once you establish, your ACL, you have to tell it where it's going to be established at, right? On that router. So ACL. So we use this IP access group command. That is what tells the router which interface to apply this ACL to. And kind of what that looks like I say, the same thing. We're going to go into the router, into the interface mode, right? Let's say we want to say on interface gigabit internet 0, gigabit interface 0/0/0. We're going to apply this ACL, okay? So then we're going to name the IPSS group, and we're going to, whatever we named it, that is what we're going to put here. Now, key thing, in or out. Now, that is determined. If you say in, it's going to look at traffic coming into the interface. If you select out, it is going to look at traffic. It's going to apply the ACL to traffic that's going out of the interface. Big difference. It changes the dynamics. Later on, we're going to get into a packet tracer where I actually show you these, and we walk through that. And what that's going to look like is kind of like these examples. So this is an example of a standard packet filter firewall. So here's what we want to do. I want to set up a rule that says set up a standard ACL rule to deny traffic to a certain computer. So that computer is here. Here's a little pretty simple network, right? I've got a router, and I have two local area networks. One here, and another local area network on this side. Here are my IP addresses and the interfaces that I'm using on that router. So basically what I want to do is take this computer, this sales workstation, 192.168.10.130, and I want to set up a deny rule where this workstation will not be able to get traffic to go into that interface. So using the kind of the schema we just showed you, first thing I want to do is set up a router config, go into the configuration mode on that router, enable the router, then go into do config T. That gets me here. I'm going to type in IP access list. It's going to be a standard one, right? And I named it no sales, meaning no sales computer. Just, you can name this anything you want. You really can. I named it no sales. Now, once I do that, now you see it takes me into another mode on my router, right? So now I'm in the configure standard network ACL. Now this is where I tell it to, I'm going to deny, I want to deny host 192.168.10.130. Okay, so now I've built my rule, and now the next line I'm going to put is called permit any. Basically, permit everything else, but deny this. Okay, so I'm going to exit out of that. Now I'm going to go into the next part. So I've built the rule, right? I built the ACL. Now I've got to apply that ACL to the interface on the router. So this sales computer, right? It is on interface of the router, gigabit 0/0/1. So now I'm going to go into that interface, int G 0/0/1. That gets me into that interface. I'm going to put this statement in, IPSS group, no sales. So basically I'm saying I want to apply the this access group named up here, no sales, and I want it in, meaning that it's going to look at anything coming into this interface on the router right there. Pretty simple. And I'm going to exit out of that. And now my access list should be set up. This router now is going to filter and deny anything for that host right there. So that's the standard. Let's take a look at an extended. Very simple, similar. Okay, so we're going to set up an extended ACL rule to deny ICMP or ping on the 192.168.10.1 subnet. Okay, same network, same IP addresses. So like I said, I've got two subnets on this network, right? I've got subnet 192.168.10.1. That's this side. And then I have 192.168.10.129 on this side. IP address schema, as you see, that's how we got those IP addresses. Now, what I want to do is that I don't want to be able to anything on here to ping. I want to shut off ICMP so that it won't ping. How do we do that? Well, very similar, just like we did before. We go into the router config. We type in IP access-list. It's going to be extended, not standard. Type in extended, and we named it. I just named it no ping, no underscore ping. All right. Okay, now that's going to, again, take me into the extended. You see it change? It's changed from standard now to extended NACL, or network access control list. And now here's where I type in, you know, the neat stuff. So I want it to deny the protocol ICMP, and I want it to deny it on 192.168.10.0. And this is the subnet mask. This is the IP. This is the network ID. If you remember from when we talked about subnetting, that's why subnetting is important, because this helps you understand this. So this is the network ID, 192.168.10.0, and I want to apply it to the subnet mask with a subnet mask of .128. Okay, so that tells the router that this right there, you know, that's the source IP address for that subnet. The any is the destination, so any destination is fine, but the source is what we're looking at right now. So that's how I would set that rule set up. I'm gonna exit out of that and do the same thing. Now I've got to configure the interface. This is on 000, right? If you look over here, yes, it's on gigabit internet interface 0/0/0. The one we did before was on this side. So now I'm going to go into INT interface gigabit 0/0/0. Same thing, access group, the IP access group, no ping, and the same thing, in. Anything coming into that interface, I want to apply this access list to. And that's pretty much it, right? Hit exit, and there you go. What we're going to do, we're going to, right after this, going to go into Packet Tracer, and we're going to walk through this in Packet Tracer so you can actually see the pings being denied as we do this. So this gives you just a sneak peek into firewalls, ACL rules, and then the last thing I want to talk about are our ASA devices. You know, if you're from a Cisco perspective, these are our adaptive security appliances. Now, what these are, it's a multi-service appliance that is primarily a component of the Cisco SecureX architecture. So what it provides a lot of things, a lot more than just what a router will give you. A router will give you the ability to do ACLs and set up firewalls. However, this will give you firewalls as well as you can set up virtual private networks. You can have remote access into it. You can set up IPS or intrusion prevention systems across these types of devices. So in a nutshell, like I said, you may see some of these, there's different families. This is just having me the 5506, you know, the 5500 family of firewall appliance I selected for this example. So if you look at this, now let's say we have a network, and how that we want to think about our networks from this perspective: inside networks and outside network. An outside network would be anything that gets you out to the internet, out to the World Wide Web. An inside network, this is going to be where we're living ourselves. This is our office or network, right? And also, again, we talked about before, a DMZ network. This is where I'm going to put things like web servers and proxy servers. And what this ASA device is able to do now, it's able to look at traffic that originates from the inside and go into the outside. It can permit that, go in that direction. It can also permit or deny traffic going from the inside to the DMZ, right? As well as it can do the same thing, adjudicate traffic that's originating on the outside and want to get to the DMZ. So like I say, we may have, maybe where you work, you have the ability from home, if you're working from home, that you want to get into the company's corporate website. That website is probably sitting here in this DMZ area. So that, boom, you can get into here. This device will let you get to the corporate website, so you can do your time card or whatever. However, if you wanted to get to other things, you may not be able to get into the inside network because of rule sets here. Or let's say this could be a public facing website, so that anybody who wants to get out to your company website, they want to see the public facing website, that would be sitting here. So they could get there from here, but they would not be able to get into the rest of the company's network. So that's what these type of firewalls appliances are able to do a lot of different things of that nature. Okay, so we covered quite a bit, right? We talked about network components and architecture. Like I said, what we're going to get into after this, we're going to go walk through some packet tracers to look at a standard ACL, an extended ACL, as well as an ASA device. So hope this helped you out. Stay tuned. Be ready to go into Module 6. All right. Have a great day.